So I'm gonna record this lecture for the lab exercise 5. I just want to make sure that we're getting a good jump on exercise 5, even though we don't meet until Wednesday. So I'll get this going, and then I'll do a couple lectures on Wednesday as well. So this lab exercise, there's a lot to it, but the actual program that you write isn't super complicated, and we're not interacting with as much hardware this time, so for what that's worth. So the objectives are to introduce the use of interrupts in input-output programming, introduce the use of multiple threads, become familiar with digital signal conditioning for interrupts. That's a debouncing circuit we'll talk about, and use TTL gates to debounce a switched input. So yeah, so we've got those things to cover. I'm going to expand on some of these in some of the future lectures, but we'll just kind of do an overview here, and we'll get you started writing your code for this week. So this exercise illustrates the use of interrupts originating from sources that are external to the microcomputer. The principal activity of your main program is to print the value of a counter on the LCD display, so the same LCD display we've been using. If uninterrupted, the counter display, which is updated once per second, would continue for 60 counts. So pretty simple program other than this interrupt business. Generally, the service of an interrupt may be arbitrarily complex in both form and function. However, in this exercise, each time an interrupt request, or IRQ, occurs, the interrupt service routine, Isr thread, will simply print out the message interrupt on the LCD screen. A push-button switch on an external circuit will cause the IRQ to occur. So our the way that we interrupt this routine is very simple. We just simply push a button, which will be on the breadboard at each station. So right now, stations 2 and 3 are the ones that are hooked up. So debug on those 2 stations. Okay. Therefore, the overall effect will be that the display will print the count repeatedly, so 1, 2, 3, up to 60, with the word interrupt interspersed for each push of the switch. So push the button, interrupt shows up on the screen, then wait, it'll still keep counting, then hit the button again, interrupt will appear, and then it'll continue to count. So that's the idea with this program. So pretty simple concept, not too bad, but obviously an interrupt could be more complicated than that. It could be some event that's happening that we want to interrupt our main program from operating whenever it occurs. So having this is a really nice way to do a lot of different things, including process control, like if this limit switch is hit, then do that, like interrupt what's happening and do some other process or some other task. Okay. Although the program is not long, it is essential that you understand the events that take place at the time of the interrupt. So 1, an unscheduled or asynchronous external event causes the activity of the CPU to be suspended, and 2, a separate section of code, or the ISR, executes before returning control to the original program at precisely the point where the execution was interrupted. So it picks up where it left off. That the counter display continues to run accurately both before and after the interrupt illustrates the main program is not altered, regardless of where the interrupt occurs in the execution. So the interrupt should be able to happen at 1 second or 10 seconds, or 10 counts, and it shouldn't matter. It should behave the same way and then continue along. So let's talk about the threads here. So there are going to be 2 threads. The main program runs in the main thread. it will perform the following tasks. As usual, open the MyRio session, then register the interrupt and the digital input that we'll use for the interrupt, and we'll expand on that in a moment. 3, create an interrupt thread to catch the interrupt. Also, we'll talk about that in more detail. Then begin a loop. Each time through the loop, wait 1 second by calling the 5 millisecond wait function from lab exercise 4. So we've used this before 200 times, so you can time it like that. And then clear the display and print the value of an int count. Okay, so and then finally increment the value of count. So counting up your int count. After a count of 60, signal the interrupt thread to stop and wait until it terminates. Then unregister the interrupt and close the MyRio session. So that's the main program kind of in broad outline. And then here is the Isr thread in broad outline. The Isr thread, the Isr routine runs in an interrupt thread separate from the main thread. It should begin a loop that terminates only when signaled by the main thread. Within the loop, it will wait for an external interrupt to occur on DIO 0. So that's the channel we'll use. The same channel we used for the PWM signal last week. So it does take a little bit of a different wiring, and I've actually wired 2 and 3, those 2 stations for this. So if you're still working on lab 4, you have to move that back over to I guess to drive the motor again. So hope that doesn't cause confusion. I'm a little worried it might. Okay, so good. It should begin a loop that terminates only when signaled by the main thread. So wait for the interrupt to come from DIO 0. So DIO 0 is essentially connected to the button, right? So when that occurs, we hit the button, DIO 0 changes. Then 2, service the interrupt by printing the message interrupt on the LCD display. And then 3, acknowledge the interrupt. So that's happening in a loop that is continuous until the main thread tells it to stop. It changes a variable that tells it to stop. So we'll expand on that in a bit. Some background. So there's quite a bit of sort of assistance in writing these because it's kind of a new concept, and there are a couple other little aspects to this exercise as well, including this debouncing circuit. So there's a lot there. So you're getting quite a bit of help on this interrupt code. So setting up main for interrupts generally. This is sort of a general guidance if you're going to be setting up an interrupt at all. And then we'll get a little bit more specific in the next section. We'll do it for our case specifically. So within main, we configure the digital input, the DI interrupt, and create a new thread to respond when the interrupt occurs. 2 threads communicate through a globally defined, so above your main, right, thread resource structure. So this is the definition. NI provides 2 C functions to set up the digital input DI interrupt requests, IRQ. So the first step is to register the DIO IRQ. The first of these functions reserves the interrupt from the FPGA and configures the DI and IRQ. Its prototype is as follows. So we call this, and this is going to sort of set it up for us. So we have to provide it with 5 things in general. We'll get more specific for our case. IRQ channel is a pointer to a structure containing the registers and settings for the IRQ IO to modify, defined in dirq.h, the header file, as being this. So you see it's got all these integers in here, count register, number register, enable register, etc. So that is already in that header file, so you don't have to include it in Yeah, as long as you include the header file, you should be fine. It'll have it in there. You don't have to repeat it in your main. IRQ context, a pointer to a context variable identifying the interrupt to be reserved. It is the first component of the thread resource structure. Okay, so go back up here. First one was IRQ channel, now IRQ context. Now we're going to talk about IRQ number. The IRQ number needs to be 1 through 8, so they're numbered. You can have multiple, obviously, 8 of them in any given channel, or sorry, any given connector. Count, the number of times the interrupt condition is met to trigger the interrupt. So we'll talk more about that. And then type, the trigger type used to increment the count. So those are the options that we have. So the different types of trigger types are rising edge, falling edge. Those are I think the only two, rising edge and falling edge. There might be others supported, but I'm pretty sure that's it for these channels. The return value is 0 for success. So you can test that if you'd like in your code. If it comes back at 0, then continue. If not, then you might want to return the status, whatever that return value is, sort of the error code. Then create the interrupt thread. The second function, pthread create, called from main, creates a new thread and configures it to service the DI interrupt. The prototype is this. So pthread create, and then we've got these 4 inputs. Where the 4 input arguments are thread, the first one, as a pointer to a thread identifier. So star thread is a pointer to a thread identifier. Thread is a pointer to a thread identifier. In the declaration here. So thread should be a pointer. Good. ATTR, which is for attributes. So a pointer to thread attributes. In our case, use null to apply the default attributes. Start routine, which is the name of the starting function in the new thread. So this is kind of a strange way of declaring this, so I'll expand on what this means. So this is, start routine is what's going to run once you start the thread. So I want to talk about why it's declared in a sort of weird way here. So the prototype syntax means the function start routine, which will be given argument arg, which is the next argument here, pointer dereferencing. So give an argument arg in the new thread. So it starts this new thread with start routine, and then it's going to hand it this arg, which is actually an argument of pthread create. So the third argument is a function. The fourth argument is the argument that's going to be handed to that function in the new thread. So it's a little weird. You don't hand the function the argument it's going to get. You hand it in separately, and then the function pthread create actually hands the start routine function the argument that you give it here. So it's a little odd, but it makes some sense once you kind of see that. So sort of parse it. It's hard to parse that line though. So in our case, it will be a pointer to the thread. Skipped lines there. So the prototype syntax means a function start routine, which will be given argument arg in the new thread, should be given to pthread create with no argument. So when we give pthread create start routine, we want to leave the argument empty. It's expecting a void. Then we'll apply that function to the argument arg inside pthread create. Actually, we don't do it. That's what pthread create does. Pthread create is something that we don't need to write. It's already defined. So yeah. So it returns 0 for success. So when it works, it should return 0. Otherwise, it'll return an error code. And setting up main for our interrupt specifically. Combine these ideas into a portion of the main code. So I'm going to give you a portion of the main code here. Needed to initialize the DI-IRQ. For interrupts on following edge transitions on DI-IO0, connector A assigned to IRQ2, we have this. So go through here. First off, we've got some ints and some other data types, custom data types that we'll declare first. And then we open the myRio NIFPGA session. So we do that first, sort of usual thing. And then configure the DI-IRQ number, incremental times, a trigger type. So then we declare these, that we actually define these as well, give them default values. So IRQ number is 2. So we're going to use 2. Count, we're going to start out with 1 as the value. We're going to use falling edge as our trigger type. And then we specify the channel settings corresponding to the IRQ channel to be accessed. So if you're going to use the DIO0 that we're going to use, we need to set all of these IRQ DIO. So this is a struct, right? And so all of these members of the struct, all the names here, will call and then assign. And so we go down the list and assign them accordingly. And some of these variables over here are used for any connector A and then a bank of DIO pins, so 0 through 7. Okay, so these are all available. I believe it's I set it here. So the IRQ channel settings, symbols, and others associated with the DI interrupt. Find in the header files DI-IRQ, DI-IRQ.h, and IRQconfigure.h. So look in those if you want to sort of expand and see where these are defined. So that is a little bit mysterious when you see them for the first time. So there are tons of them, and we're using just a subset of them for using an interrupt on DIO0. So if you wanted to do multiple, you would need to add something similar to this. But if you want to know where they come from, essentially they come from the header file, and you just copy and paste them in accordingly. You could try retyping them, but then for me, I'm going to misspell something. So just copy and paste. Okay. Initiate the IRQ number resource of interrupt thread. So this is IRQ thread 0 struct. We're trying to IRQ number, which is a name of a member of the struct, to IRQ number, our variable, and then register the DIO IRQ and terminate if not successful. So we register it using the IRQ register DI IRQ function. And we just hand it these arguments here, and if it's not successful, we'll return the status of the error code. Set the indicator to allow the interrupt thread, so IRQ thread 0, IRQ thread ready should be true, so that means we're signaling to our interrupt service routine that we're good to go. And then create interrupt threads to catch the specified IRQ numbers. So this is the pthread create. That's the pthread create function that we were just discussing. So here are the variables based on what we've written above here. We need to hand to pthread create. So kind of like that's all kind of given to you in a sense. So I want you to make sure that even though the code's given, that you try to understand it at some level of depth. Obviously, you don't need to understand the details of every aspect, but try to understand it to some level of depth. Part of the report will actually be describing this, so you should be able to understand what it means. Great. And then finally, so put your other main tasks here. So These ones above are finished, so then before you close your main function, you have other tasks to complete. So it should signal the new thread to terminate by setting the IRQ thread ready flag in the thread resource structure, then wait for the thread to terminate. For example, you could do something like this to terminate it. Finally, the interrupt must be unregistered. So this is after, right? So all this happens, and then you do your other main tasks, and then this is sort of closing it out, right? You're closing up shop now. So unregister DIIRQ using the same above arguments to use the pthread functions. Make sure that you include pthread.h in your code. Good. The ISR thread. So we've talked about the main thread. Let's talk about the ISR thread. So this is the separate thread that was named and started by the pthread create function. So pthread create, we had that up here, right? So pthread create. So this part of our main function. Its overall task is to perform any necessary function in response to the interrupt. This thread will execute until signaled to stop by main. The beginning in which we do right here, right, by setting IRQ thread ready to NIFPGA false. That's how we signal to it. Great. The beginning of the new thread is the starting routine specified in the pthread create function called in main, which is this, which has this prototype. So this is the prototype for it. The first step in DIIRQ thread is to cast its input argument into appropriate form. So you have to pass it in this sort of weird way using that strange syntax, right, where the argument was not attached to the function. So we need to now sew them back together, but well, what we need to do is we need to extract the information that we want from what we pass to it. So we have to cast it into the appropriate form. In our case, we can cast the resource argument back to the thread resource structure. So we can take the resource that came in as the argument, and we can cast it using thread resource star and the cast operator parentheses, and then assign it to thread resource. The second step is to enter a loop. 2 tasks are performed each time through the loop, as described in algorithm 3. So let's look at algorithm 3 here for a minute. So this is some pseudocode. So this is the thread loop. So there's a main while loop that's going through and doing the counts, right? And then the thread, the ISR, interrupt service routine, it's got thread a loop as well, and here's what the loop's doing. So while the main thread has not signaled this thread to stop, do this. So it's going to just keep going through this until it's signaled to stop by the main thread. So it waits for the occurrence or timeout of the IRQ. So it's waiting for somebody to hit the button or to time out. If the numbered IRQ has been asserted, so that's the button being pushed, right? Perform operations to service the interrupt, and which is to say print the interrupt on the LCD screen. And then acknowledge the interrupt, and we'll talk about how to do that. Then end your if statement, and then end the while statement. So once you exit the while statement, then it's done. So this thread is a dead thread then. So let's explore how to do this. The while loop should continue until the IRQ thread ready flag set in main indicates that the thread should end. For example, we could have a while loop that looks like this. So it's a little bit of a weird syntax, but essentially what it's saying is, as long as IRQ thread ready is true, keep doing stuff in the ISR. So in the ISR while loop, just keep going. This here, so a little note on this syntax. So what we have is a struct thread resource, and and actually what we have is thread resource is if we go back up here, thread resource is a pointer to a thread resource. So if we want to find out actual values from that thread resource, we could dereference it and then do to get IRQ thread ready, we would do dot notation, right? Thread ready. And this syntax would totally work. So if we did this, that would be totally fine. This is a bit of a shortcut. So if you have your variable that's not the struct itself, but it's a pointer to the struct, instead of having to dereference it and access the contents by name, like we usually do with a dot, then we can use this nice right arrow operator where it's a dash and then I don't know, right caret. I'm not really sure what that symbol's called. Greater than symbol. In any case, that's the syntax for it. So it's a bit of a shortcut notation, but I know there are so many sort of shorthand notations in C that it can be a little hard to parse sometimes. So that's something to keep in mind. So while this IRQ thread ready, which is set in main, is true, continue this. The two tasks within the loop are as follows. Use the IRQ wait function to pause the loop while waiting for the interrupt. So we already have this IRQ wait function kind of built for us. So we hand it the thread resource, IRQ context. So that's, once again, that same notation. So thread resource is a pointer to the thread resource type, which is a struct. And then get the IRQ context name contents from it. And then here you need to actually make a pointer out of IRQ assert, which you define to be 0 here, but we'll talk about what happens within IRQ wait to that. And the reason we handed it a pointer is that we want the function IRQ wait to be able to write to IRQ assert. Okay. And then we've got once again this Boolean version as well. So this is the fourth argument. So notice that it receives the thread resource context and IRQ number information and returns the IRQ thread ready flag set in the main thread. So IRQ thread ready flag is something that we can get from main, so we can stop waiting if the main function tells us to. Because IRQ wait times out after 100 milliseconds, so this is actually, we wouldn't have to test for what IRQ assert is if we were waiting until there was an interrupt. So IRQ wait returns. Sometimes it returns because there was an actual interrupt. Other times it returns because it timed out, after 100 milliseconds, which happens 10 times a second, so it happens a lot. So we have to test. So we must check the IRQ assert bit flag. So IRQ assert, we handed it, we defined it to be 0 to start, and then we said, okay, we handed it to IRQ wait, we handed a pointer to IRQ assert, and IRQ wait is going to write to IRQ assert and tell us the number of any IRQ that happened, or not. If it just timed out, it wouldn't set that. So we have to check the IRQ assert. But IRQ assert is a very special type of variable. So it's not just a well, the easiest one would of course just be an int that we could say 0 or 1, right? But it's very common to use bit flags, and this is IRQ wait treats it like a bit flag, so we also have to treat it like a bit flag. So let's talk about bit flags for just a second. And then this is footnote 9 here. So a bit flag is a bit of independently useful information stored in a larger integer variable. So because a byte is the smallest addressable unit of memory, of course, multiple bit flags can be assigned to a single integer variable. So if you think about it, so a flag need only be able to store a 0 or a 1. So it really only needs one bit, right? Like if you had to say like, did the button get pressed, it needs to represent a 0 or a 1. You only need one bit for that. But the smallest addressable unit in memory is a byte, right? So if we have 8 bits in a byte, then you're wasting 7 of those bits, essentially. And that's kind of a shame. So what we'll often do, if you've got embedded situations where you've got a limited amount of memory, is that you'll use a bit flag. So you'll say, okay, in my byte, I've got say 4. So let's say this is a nibble, maybe a little bigger, a nibble, and then another nibble. So there's our byte. We'll use all 8 of these bits for different flags. So they're not related to each other necessarily, but they might be represented by, say, they might represent, say, like an 8 pin bank of a connector would be a good way to go with it. So our IRQ assert bit flag could be, just any one of these could be our one corresponding to a given pin. So actually, in this case, IRQ assert is going to what it's going to do is, well, what this function IRQ await will do to IRQ assert is it's going to flip the bit associated with the IRQ that was asserted. So if IRQ happens on say 2, channel 2 for instance, then it would be like 0, 1, 2. So like the third bit would get flipped from say a 0 to a 1. And that would be our indication that something happened on channel 2. So that's what we have to test for. So it's a little bit weird. We have to use bitwise operators. So here is the if statement that we could write. So it's a very sort of strange thing. So we take IRQ, there's the thread resource. So I've been saying channel, but I really meant IRQ number, so my apologies on that. The thread resource, we extract out the IRQ number, which we set to 2, right? That was what we set it to, I think. Back, we set that. IRQ number 2 up here. So we're looking for IRQ number 2 to be flipped. So yeah, so 2. And this is one of the bitwise operators that C gives us. It's called left shift. Okay, so what it does is it takes the integer byte so it takes the whole binary number that's represented that represents the integer literal 1, which is going to be a bunch of zeros and then 1, and it's going to move it left however many times the number is here. So it's going to move left 2 times in this case. So 0, zeros, so 0, and then it's in this first position, so it needs to move over 1, 2 times, so it'll be 1, 0, 0 is what this does. And this is called, so this is, what this has is it has a 1 in the location corresponding to the IRQ number that we're interested to test to see if the flag was flipped by our IRQ weight function. Okay, so hopefully track it. It's kind of a tricky one. And we can talk more about this next week. So now we want to do this AND operator. So the AND operator, when you so this is the bitwise AND. So AND logic AND is going to be 2 ampersands, but this is 1 ampersand, and what it does is it compares bitwise with whatever IRQ assert is. So if IRQ assert is a bunch of zeros, say, and then once the interrupt happens for IRQ number whatever it is, it flips that bit. So if it so happens that that bit is flipped, then when you do the bitwise ampersand, bitwise AND, it's going to do logical AND bitwise. So 0, 0 would give you 0. 0, 0 would give you 0. 1, 1, so 1 and 1 is true. 1, 0, 0, 0. Okay, so this is the result. Now, imagine that IRQ assert had flipped multiple of them. There were multiple interrupts that happened, but you only really want to test for the IRQ number that you wanted to test for. That's what the AND's doing for you, because you're masking out. So even if, say, this one right here was a 1, maybe that one was flipped also, we're masking that out because 1 and 0 is still 0. So the only one that can come out here is that guy. But if it's not been triggered, then this will be 0 and it'll mask to 0. So this is thing that is always going to come out to 0 unless the interrupt came through with the corresponding IRQ number. That's what we want to test for, is did that IRQ number, did that interrupt happen? If it did happen, we're going to get a 1 somewhere in here. And if it didn't happen, we're not going to get a 1 somewhere in there. Now, you might say, okay, well if, and then it's going to be some integer, so this is going to be, zeros, and if it happens, so if it doesn't happen, first off, the easy case is if it doesn't happen, it'll be all zeros, so that represents, so that's 0, and if you say if, and then you hand it an integer as the comparison expression, or as the conditional expression for if you hand it 0, it evaluates that to false, right? So if 0 doesn't execute the if statement. But you might be thinking, well, so if this comes out to be just a 1 here, 0, 0, 0 in binary, and then 1 at the very end, that's evaluates to 1, which is true, right? So if true, and then it does evaluate the statement. But if it shows up over here, then this is like 5 or whatever it is in binary, or represented a decimal. So if 5, what's that going to do if you had an integer 5? And actually, so C is going to evaluate any integer that's not 0 to be true. So 5 would evaluate to true, and it would run the if statement. So it's this is a very simple looking expression, but there's a lot packed into it. So hopefully that expansion on it clarifies some things. The third step terminates the new thread and returns from the function. So this pthread exit function, you hand it null as the argument and return null, and you're done with your ISR. So here's the procedure. So build, debug, and execute your program. Provide interrupt signal by connecting the single pole double throw switch on the circuit board to DIO 0 of connector A as shown in figure B7. So figure B7, oops, it's up here. Figure B7 is this. So this is a single pole double throw switch. So what it does is the simplest switch is a single throw, so So single pole, single throw switch, which is just to say it disconnects two terminals or it connects those terminals. That's very useful, but actually a more common switch to see, and actually those buttons that we put on for the last lab 4, were actually of this type. So single pole, single throw. The next level up, which is actually more common to see, is a single pole double throw, which is this setup here. So what you have is 3 terminals, and it can switch. Essentially, if you think of this as being, even though it doesn't have to be the output necessarily, think of this as being the output. It can switch between either this input or this input to connect with that output. That's one way to think of it. Or you can think about, with one input, you have 2 possible outputs. You can think of it that way too. And the switches that we have actually have 6 terminals, which is pretty common to see. And 6 terminals, the other side is just a mirror image of it. So actually not a mirror image, it's a reverse image of it, a rotation. And the rotation gives you another, so it throws both switches when you push the button, so they're not totally independent of each other. But you can control multiple circuits with just one switch if you want. So, but what we're going to do is just actually, we have to be careful of, in the breadboard, when you put it in, it actually connects these. So what you do is you cheat and you bend. I just bent. You can actually cut it off, but you bend one terminal like this, so that when you connect, if you bend this one up, then no matter which when you connect, this is a dead end, right? So open circuit. So you bend the one, or you cut the one that is connected to the sort of base of the switch. So that's what I did. Otherwise, you would have not the circuit that you thought you had, I guess. Yeah. So enough about the switch. You have the switch in there. So I think this is the switch. And if we connect simply in this first, so we're going to do 2 cases. In the first case, we're going to just connect this thing as a single pole, single throw switch. So we're just going to connect it to the DIO. We're going to connect DIO to ground through the switch like we did last time, which is going to pull it low, and that'll be the falling edge trigger for us to our interrupt request. But there are issues with that, and so that's what this whole debouncing thing will be about. So good. So first, do it this way, in this sort of naive way. Connect it up so that it switches to ground like this, and we have this interrupt occurring. So try it and see what happens. This undesirable phenomenon is called the bounce of the mechanical switch. So what's actually happening is your switch closes, and actually mechanically it comes into contact, and then it bounces. It actually literally comes out of contact, and then back into contact, then out of contact, and back into contact several times. There's a question of how many times. So you're going to be able to see this phenomenon occurring on the oscilloscope. So take a look at that. I've set up the probes so that they should be better on the oscilloscope this time. There was some weirdness in the last setups that I saw for the probes. So alligator clips and a BNC cable should be set up now for you at stations 2 and 3. And so we've got this bouncing that's happening, and clearly that's not what we want. We don't want every time we hit the switch to have it like switch back and forth a bunch of times. That's sending a lot of interrupts to the program. And that's not what we want to have happen. So adjust the oscilloscope to examine the high to low transition to IRQ. Typically, what length of time is required for the transition to settle at the low level? How many TTL triggers occur during the settling? So when you do this, you're going to see it go a bunch of times. So about how long does it take to settle down, and how many times does it go up and down? Correct the problem by replacing the switch in figure B7 with the debouncing circuit shown in figure B8. So figure B8 is right here. So we still have the same switch in there in the circuit, but we added some stuff. Okay, so I want to expand on this in I'll do another lecture this week where I'll expand on this, and we'll talk about what all of these components are. These are actually gates. Okay, so we have to talk about gates and discrete logic and all that. So we have to have a discussion about that. I don't want to get into the details now, but the idea is that this is going to help debounce your circuit, and we'll do a little lecture on debouncing and the logic as well. So it'll be kind of cool. I just think it's really cool. It's a very, very, very clever, like incredibly clever. But you'll get it too, so it's cool. Correct the problem by replacing this with the debouncing circuit, which includes the switch as well. So this circuit incorporates a TTL open quad collector NAND gate 7401. So actually, these are two NAND gates, and so the TTL 7401 is an integrated circuit here that we are going to plug into a breadboard. Actually, it's plugged in already to a breadboard. And you can use its NAND gates. It has 4 NAND gates on one chip. So we're going to use 2 of those NAND gates, and you guys are actually going to build this circuit yourselves on the breadboard. So first you'll connect the switch directly up to your channel 0, and then you'll connect the NAND gates and this TTL through this TTL 7401 and a couple of resistors to which are, by the way, already on the breadboard. So some of this is built for you. So you've got this on there already, you've got the switch on there already, and you've got the resistors on there already. All you need to do is properly connect the gates. So, and actually the power and ground are already connected on the 7401. So don't disconnect the power to the 7401. It's already there. But you're going to add some connections. You're never taking away connections. You're only adding connections. You're going to add some connections between, so connection A, connection B, and then connection at Q and connection at Q star, then to channel 0, to DIO 0. So those are the connections you will make on your breadboards to incorporate this circuit. Try to be careful with this. There are some things, I mean, you're not going to blow anything up, but there are some things you could do to damage these circuits. So it'd be nice. That didn't happen because I don't have any spares right now, so I'm ordering some. So try not to fry anything. If you do, it's okay. I really won't be mad. Just please tell me if you do, if you melt something, because then I will know to fix it. Otherwise, I don't know to fix it. I'm a pretty forgiving person. I'm not going to be mad if you tell me that something is broken. I would appreciate it you told me. Okay. Caution. So this is the caution box. Be sure that the VCC and ground are connected to the chip before wiring the rest of the circuit. So these are connected on stations 2 and 3. So on the breadboards, ground's already connected to channel 7 here, and VCC is already connected to channel 14. However, double check to make sure that they are there, and don't disconnect them if they're not. If they're already there, don't disconnect them. So leave them be if they're there, but make sure that they're there. Okay, try the program again, and then explain in detail why the circuit should solve the switch bounce problem. That is, graph the time history of signals at points A and B, so on the circuit, points A and B, that would occur during the operation of a bouncing switch. Then graph the corresponding signals at Q and Q star, so the inputs to these NAND gates, and then also plot the outputs. Finally, in your own words, explain how the main thread configures the interrupt thread, how it communicates with the interrupt thread during execution, and how the interrupt thread functions. So this is the part where I gave you a lot of code and I gave you a lot of the circuit, but you're going to have to explain to me in the write-up how these work. So hopefully that gets you started. Don't delay in getting started. I know Lab 4 has been a challenge for a lot of you guys, so it's fine that people are running a little bit behind, but we do have a lot coming up, so I really want to get Lab 5 done this week, so we're ready for Lab 6 next week. So, all right, take care.